final exam it'll be 2 hours for the final exam, and I'm not sure how many problems we should put on the exam, but I already posted 2 sample final exams, and there will be 14 problems on each of them. Okay. So if we reduce the number of the problems, then we have to increase the number of the points for each problem. So final exam total will be 200 points. Okay. This is comprehensive final exam. Okay, it covers almost all the material. Okay, so I'm going to go through the problems on the first sample final exam. Okay. Now, when you take the test number 3 back, please check my grading, and if you have questions, please talk to me. Okay. So the first problem we're going to discuss is we are given a quadratic equation. We want to find the equation tangent to the point. Okay, find the tangent to the plane. So this is a find the equation for the tangent of plane. Okay, to the surface at the point 1, 1, 1. So first, to make sure this is a point on the surface. Now, there are many ways to find the tangent plane. Okay, if it's graph of some function, then we have a formula for the tangent plane to the graph of function, which we already learned that, I think in Math 160. Well, yeah, earliest chapters. So here, yeah, this equation means actually the surface described is actually just the level surface of a function. So you let f x, y, z to be x squared plus 2y squared plus 3z squared. Okay. Okay. Then the equation becomes f equals 6. Okay. So this is kind of like a level surface in the space. What we know is at every point, okay, the gradient of the function at every point, okay, is going to be perpendicular to the surface. We should know this fact. Then we use a normal vector to get normal vector to the surface, which is normal vector to the tangent plane, to get the equation for the tangent plane. Okay. So this is a perpendicular to the surface. Okay. So let's find out. Okay. So here the point is 1, 1, 1. Okay. 1 and 1, right? And then we find the gradient. Gradient of the function is going to be 2x, 4y, and 6z. Okay. Okay. So when you evaluate at that particular point, you get 2, 4, 6. So this is a normal vector. So you know now you know the normal vector, you know the point, and you can get the equation for the tangent plane. Okay. And the arbitrary point here, x, y, z on the plane, if you look at the difference, okay, from this fixed point to that point on the plane, this is a tangent vector to the surface, which should be perpendicular to the normal vector. So the equation will be x minus 1, y minus 1, z minus 1. That should be equal to 0. That's just perpendicular to each other. Okay, so here will be 2x minus plus 4, y minus 1 plus 6z minus 1 equals 0. Now, if this is a graph of a function, right, how do you find the tangent plane? Okay, for the graph of function, there's another way to find the tangent plane. Okay, yeah, for the graph of function, z equals f of x, y, right? And then it's just a graph. Okay, and so you can parameterize the surface using the function. So you have R. You see, use user knowledge from the last chapter. It's going to be x, y, f, x, y, right? Right. And then R sub x is going to be tangent vector, and this will be 1, 1, f, x, right? Then R sub y is going to be 1, 0, 0, 1, f, y. Okay. So those are two tangent vectors. How to, if this is a point x naught, y naught, z, right? How to find the equation for the tangent line? There are two different ways to find it. You can find the normal vector, right? Use a normal vector. It's not necessarily the unit normal vector. It's not necessary, okay? Just cross product. And you will see that this will be fx negative y and 1. Okay? You can normalize it. I'm not, yeah, this is it's not necessary to be unit vector. So just that's perpendicular to the tangent plane. Okay? So the equation for the tangent line at that particular point, where z equals f naught y naught, right? Is given by the following formula. First of all, the normal vector right? Dot product x minus x naught, y minus y naught, z minus z naught is going to be here. Okay, so it's the same idea. Okay, so I just give you the formula. You know, if maybe the equation is the surface is a graph of some equation, this is what you get. Another way you can describe the plane. Plane is think about the plane is going to be a surface also. How do you describe a point on the plane, right? The way you can describe it is take an arbitrary point, okay, on the plane, and you look at the difference. This vector should be linear combination of those two tangent vectors. So another way you can show is I'm going to use a different notation, okay, for the tangent plane, u and the v. So this is going to be the point. Okay, plus u v. Okay. Now what does that mean? That means for an arbitrary, now this is surface again, okay? So this is a point x naught, y naught, z naught. And a tangent plane, and this is a sigma u and v. Okay, this is the origin. Right. The difference should be linear combination of these two vectors. Right? This is y, this is x. Okay, so just linear combination of it. Okay, so now you parameterize the tangent plane using two variables, u and v. U, v, and arbitrary. Okay, right? How to describe that point? It's a sum of the two vectors. The first vector is from origin to that point on the plane. Then the second vector should be linear combination of the two tangent vectors. All right, that's all about the tangent plane. Yeah, you can practice to solve the problem using the following. Okay, here's a question I did. I find the tangent plane to the surface. Okay, z minus x squared minus y squared equals equals -1 at 1, 1, 1. Okay. You can have multiple ways to solve this problem. You can view this surface as a graph function. You can also view the surface as a level surface of some function. Okay. Okay. Then this is a there are two different ways to find the tangent plane. All right. So second problem I want to discuss is sketch the region of integration, okay, and change the order of integral. Now, sometimes you are asked to express the double integral as two iterative integrals in both ways. Okay, then you have to give me the two integrals. Right. So you really need to understand how do we get this iterative integral from a double integral. Right? You have to find out the region of the integration. Okay, otherwise you cannot just switch the order. Okay, so let's understand this iterative integral. It's somehow a double integral of the function in dA, right? So we have to figure out d. Now from this iterative integral, you will see that there's no restriction on the y variable, right? Because y is all. See, look at the y. dy is all sides. Y is from 0 to 2. So from 0 to 2. So y is an arbitrary point y between 0 and 2. Then you draw the horizontal line, but for the x, for each fixed y, x is going to be, first of all, x is between 0, right? Yeah, this side is y between 2 and 0. Here, for each fixed y, x is between 0 and the y squared. So what is y equals x squared? Y equals x squared is going to be this parabola, right? Y equals x. So x equals y squared. X equals y squared. So x is between 0 and y squared, so it's going to be this piece, right? So that's why you get the domain D. Right? So you determine the region first. Right? X is between 0 and y squared. Then you find the intersection point. So when y equals 2, and when y equals 2, what is the x value? X value is going to be 4, right? So now you're going to use a vertical line to partition the region. Okay, so what they're going to do is for an arbitrary, so let's draw the picture again. So this is the region. Here's a 4, this is a 2. Okay. Okay, so you x no restriction for x. So this is going to be from 0 to 4 dx, okay? Then for each point x, you draw the vertical line. And then y is clearly between those 2 points. Okay, what is the y? So y is actually the top one is too clear. But the bottom one depends on x. Right, this line is x equals y squared, so y equals square root x. So for the fixed x, the y value is going to be square root x. That's what square root x. Okay, so we switch the order. Okay, so you are using the vertical line. Right? Yeah. Step 1, you choose determine the interval for the x variable. Right? Then put x outside. Then you draw for each x you draw the vertical line and you see the line segments in the region. Then you determine the range for the y variable. Yes.
If it went from 0 to square root of x, is that correct?
That's you being incorrect. Now that would be the integral over the region under this curve. That's totally different. See? Right? You are integrating the function over the region, not over something else. So you are going to integrate. What you're going to do is you integrate along the line segments inside the region. Okay. Okay. So express the double integral right d okay as iterated integrals into in both way, okay, in both form. So here's a region. Okay, let me show you the region. Okay, so the region is going to be this part. Okay, this is a parabola. Sorry. This is a portion of the parabola y equals x minus 1 square. Okay, x is between 0 and 1, right? Right. So the region clearly is 1. This is the region I described already. Okay. The curve is given by this equation y equals x minus square. Now, can you express this double integral in as iterated integrals in 2 different ways? Okay. First of all, you use a horizontal line segment. Okay. So using horizontal line segments, so for each fixed y variable, you draw the horizontal line segment. There's no restriction on y. Y is from 0 to 1. Right? Y is from 0 to 1, dy. Then you integrate the function along each horizontal line segment. And clearly the upper bound for x, you see, what is x, right? X is between those 2 points. I'm sorry. X is between those 2 points for the fixed y, right? So the lower bound, the upper bound is clearly 1. The lower bound, you have to solve for x in terms of y. So y equals, this is the point, right? This is coming from the point. This, yeah, it's the first coordinate of that point. And x equals x minus y squared. So x minus 1 is going to be square root of y, but you have to move 1. So this is the lower bound for the x. Okay. Now, if you want to use vertical lines to integrate the double integral, then x will be between 0 and 1. Okay? For an arbitrary point x, okay, what is the lower bound for the y? Okay, upper bound clearly is still 1. Okay, the lower bound, if x is fixed, what is the lower bound for the y value, for the line integral inside this region? The lower bound for y variable is determined by this curve, which is going to be x minus 1 squared. Okay? So the third problem is to evaluate this triple integral 2y dv. Right? E is going to be x, y, z. Y is between 0 and 1, no restriction y. X is restricted. Okay, it's between 1 y squared, and the z is between 0 and x. Okay. So it's clearly 1 by 1. So no restriction y, x restriction on x depends on y, and then the restriction on z depends on x. So z should be the inside. So first of all, y is between 0 and 1. Right, dy. And for each fixed y, x is between 0 and this, yeah, right? And for the z is between 0 and x. Okay. Yes. All right, so then you step by step to evaluate. Okay, I put a similar problems on the quiz, you know. Right, step by step. So there's 2y is independent of z. So that's the reason it's 2y. Be careful when you evaluate the integral right there. Antiderivative. Don't be confused about the variables. 2y is independent of z. So 2y is a constant with respect to z. Just 2y. Then the difference between x and 0 is just x. Okay. The next is here's 2yx. Y is a constant with respect to x. But you have a 2x. Antiderivative of 2x is x squared. So y and x squared. Right. Then you evaluate this. It's going to be square root of 1. It's 1 minus, yeah, it's 1 minus y squared. Okay, dy. Okay. Then you multiply this out. It's y minus y cubed dy. The antiderivative half of y squared, a quarter y to the fourth from 0 to 1. That's going to be 1/2 minus 1/4. Okay, and look at the sign. When you get there, here's positive. But if you go back to integral, I think it's going to be positive. Now, the question is, it's hard to draw the region, okay, in 3-dimensional space. Okay, it's not easy to draw it. Okay, it's not required. Now, sometimes you are given the region and you have to evaluate the triple integral. Then you have to choose. Sorry. I'm not. sometimes you are given the region, okay, not by encode, you're given the region. For example, if you still evaluate the triple integral 2y dv, and E is bounded by, we say bounded by the surfaces. Bounded by, for example, the cylinder, okay? So x squared plus y squared equals 1, and z is between 0 and yeah, z is between 0 and let's just make it easier, just between 0 and 1, okay? So this is the region is this piece of cylinder, okay, cylindrical container, okay? So you're going to evaluate the triple integral, okay? So in this case, clearly, you should break this triple integral to a double integral. The double D is the domain D. Then here's dz, this dx. Okay, and for each point in the xy plane, and you draw the vertical line segment, and you look at the range for the z, and clearly z is from 0 to 1. Now, the upper bound could be a function, right? Sometimes we use a plane to cut the top part, okay? And then that's 2y, okay? So the first step is to evaluate, yeah, what is the d? D is going to be the circle, the discus in the xy plane, okay, which is the bottom disk in the xy plane of the cylinder, okay? So this will be D, and the 2y here, 2y is constant with respect to z. So that's why I take 2y out. The integral of 1 from 0 to 1 is just 1. Then you use the spherical polar coordinates from 0 to 1 and from 0 to 2 pi to r cosine, no, sine theta, and then r d theta dr, okay? So this is y is r sine theta, right? But clearly, this integral is going to be 0 because the integral of sine theta from 0 to 2 pi is going to be 0. Now, that was, yeah, so, yeah, this, you have to use the polar coordinates to simplify. Yeah, otherwise it's very complicated. Right, it is going to be 0. Okay, so you can use, yeah, iterating, triple integral can be expressed as iterative integral of one is a double integral and one is one single integral. Okay, now, yeah, let me show you another problem similar. Okay, so evaluate the triple integral 2I dA dV. Okay, and here is a domain region E. Okay, that is this region. Okay, this is a it's a solid. Okay, you have a 1, 2, 3, 4. It's a tetrahedral, right? It's called, yeah. So you have 1, 2, 3, 4 faces. So this is a E. Okay, how do you evaluate this integral? I think here's a 1, 0, 0, 0, 1, 0, and 0, 0, 1. First, you write down the equation for this plane. Okay, so the equation will be x plus y plus z equals 1. Okay, so this plane can be viewed as a graph of any of these functions. Z could be equal to 1 minus, yeah. All right, so how do you evaluate this integral? Okay, you can so always I always begin with a double integral. Okay, so I choose this d at the bottom. Okay, that is my d. Okay, so d is in the xy plane. Okay, that is my d. All right, now this equation of the line is going to be x plus y equals 1, right? Okay. So this is a d. For each point in the domain d, you draw a vertical line. All right, so this line segment is inside the solid. Okay, so that piece you have to determine what is the lower bound for the z. Lower bound for the z is 0. The upper bound for the z is determined by this equation because this is the plane, the graph of function. So it's 1 minus x minus y. Okay. Right. Then you evaluate this. It's going to be 2y, 1 minus x minus y dA. Next step is the double integral. This double integral can be now expressed as iterative integral. So you can put the x outside or y outside, doesn't matter. Let's put the x outside, then dx. Okay. I prefer to put the y outside than dy. Okay, because it's an integral. Okay, so you use a horizontal line now if it's a y is outside, right? Y is between 0 and 1. And for each fixed y, what is x? X's lower bound is 0. Upper bound is determined by this equation again. It's 1 minus x. 2y, 1 minus x minus y dx. So you just evaluate this polynomial. Okay? For this polynomial, yeah, I got 2y, 1 minus y, this constant, minus 2y times x and dx, dy, right? So this is there is only one term containing x. Yeah. 2y times 1 minus x, 2y times x, yeah. So it's 2y, 1 minus y, and then it's constant. When take it out, there's 1 minus x, minus y, that would be x squared. X squared. Hold on. No, this is a y, not x, okay. Yes. Yeah, for the fixed y, the upper bound for the x is going to be 1 minus y. I'm confused. Okay, so this will be y, and this will be x squared. So 1 minus y squared. Okay, and dy. So that's just a polynomial you can evaluate. So actually, you will be surprised that 1 minus y, so you have 1 minus y, so 2y, so it's just y, 1 minus y squared dy, okay? And you continue, it's y, minus 2y cubed, minus 2y squared, yeah, plus y cubed dy, so the entire derivative will be, okay, and I can quickly write down, okay? Right, so there are two different type of triple integrals. You should know how to do it. And sometimes you are given the region, sometimes you are given the coordinates for the region. Okay, So problem number 4. C is described by by this parametric equations. Okay. So by definition, right, you have to figure out what is the S, ds, right? So you can write down the formula directly. It's going to be from 0 to 1. X is t, okay, along the curve. ds is going to be x prime t squared, y prime t squared dt. That's the ds, right? Then the next step is to calculate, and what is x prime? It's 1. What is y prime? Is t squared. And once you get that, you just use the just use substitution. Okay, so it's going to grow when t equals 0, that is 1. When t equals 1, that is going to 2. And du equals 2t dt. So this will be u to the 1/2. T times dt is half of du. Okay, and the entire derivative of this will be 3/2 u to the 3/2. Okay, evaluate as 2 endpoints. Okay, that is going to be 1/3. 2 to the 3/2 minus 1. Yeah, you cannot simplify it further. So given 3 points, those are 3 points in the space. We want to find a vector orthogonal to the plane. Right? This plane through P, Q, and R. Okay. B. Find the area of the triangle PQR. That's 2 questions here. Okay. So we have, I just sketched the graph, okay? So where's the P? Somewhere here. Q, somewhere here. And R, somewhere there. Okay. So we are going to find a vector orthogonal to the plane. Well, to find a normal vector to the plane, you just needed to find these 2 vectors, right? So the first vector, let's call it U. Second vector, called it V. Right? And it's a cross product with perpendicular to the plane. So U is going to be the difference of those 2 points. Let me put the coordinates here. 1, -2, 1, 4, 2, 1, and -1, 3, and 2. So the difference of those 2 points will be 4 minus 1 is 3, 2 minus -2 is 4, 1 minus 1 is 0. V is the difference of these 2 points. -1 minus 1 is -2, 3 minus -2 is 5, and 2 minus 1 is 1. Okay? So you get 2 vectors. The cross product of 2 vectors is going to be another vector perpendicular to that, right? So U plus V. We're looking for a vector. That's a vector. This will be perpendicular to plane. Okay, the triangle. in this. So yeah, just find the IJK 340 negative 251. Okay, the first component is going to be 4 minus 0, just 4. The next component is 3. Okay. Okay. And the last component is 15 plus 15 plus 8. Okay, 23. So this is a vector perpendicular to the plane, to the triangle. Now to find the area of the triangle, find the area of the triangle. Look at the triangle, right? The area of the triangle will be half of the area of the paraboloid. If this is a vector u, that's a vector v. Remember, the norm of these two vectors, okay, is going to be, if this is the angle theta, this is going to be sine theta. Okay. So this is actually the area of parallelogram. Why? Because use this one as a height, right? So it's going to be the length times the height h. So that is the area of parallelogram. Okay. So the area of parallelogram, okay, spanned by u and v. So the area of the triangle PQR is going to be the half of that. Okay, so this is going to be 1/2 of the components 4 and 4 squared plus negative 3 squared plus 23 squared thing. Yeah, if there's no computation mistakes, this should be the right one. Okay. All right. So number 6. Find the limit if it exists. Okay. Otherwise, show that the limit doesn't exist. I think the limit exists. It's going to be 0 because the degree of the polynomial, the numerator is 3. The degree of the polynomial in the denominator is just 2. So the numerator approaches 0 fast. Yeah, the question is how do you can try different paths toward the origin. You always end up with 0. But this is not a proof for the limit, okay? My claim is, yeah, for example, if you along the x-axis, okay, and you will see that x squared y over x squared plus y squared is going to be t squared 0. Okay, this is already 0. It's approaching 0. So along the y-axis, it's also 0. Now along the line in the middle, x equals t, y equals t, or any line, okay? Any line. So I have A and put a B there. Arbitrary line, right? So this is A and the B. So this is an arbitrary line. Along this line, I'm not getting, yeah, it approaches to 0, right? Let's see. The function is going to be A squared T squared BT AT squared plus B squared T squared. All right. So after you cancel the T squared, you get a squared b and the t. And clearly this can be 0 as t approaches 0, okay? But this still does not guarantee the limit is going to be 0. Okay. This does not guarantee. You only guarantee along each path toward 0. Strict path, okay? Toward its origin, the function approaches 0. So I claim, I conjecture, it's not a proof, okay? Right? But that, so if you just jump to the conclusion, say it's 0, and you'll not get the full credits, okay? Because your argument is not proof. Your argument only proves the following fact along each strict path, okay, not curved path, okay, towards the origin. The function approaches 0. That's it. But this is still not the definition of the limit as x approaches 0. Oh. The screw does not work, so I cannot see. Now it dropped the bottom. Oh, that's technology. Very careful. All right, so this is this is just a conjecture. We can only make a conjecture. Now, how do you prove the limit is going to be 0? You need the following important inequalities. Right? This inequality, you may need it. 2xy is less than or equal to x squared plus y squared. Right? Absolute value. All right, and why this is true? Why this is true? Because x squared plus y squared minus 2 absolute vector minus y. This is going to be this square. So this is always equal to 0, greater than or equal to 0. All right, so now x squared y over x squared plus y squared is going to be absolute x, absolute y, and x squared plus y squared. And this one, I know it's less than or equal to 1/2. Okay? So 1/2 times absolute x, clearly this approaches 0 as xy approaches 0. Because when xy approaches 0, x approaches y approaches 0, of course. Okay, so therefore we conclude that this is not a conjecture, this is a proof. X, y approaches 0, 0, x squared y is going to be 0. Right? Use a stock theorem to evaluate this line integral. F is going to be y squared I z squared j and x squared k. C is a triangle and with vertex right, oriented counterclockwise. Okay, this is a triangle. So we did this type of problems many times. I'm going to repeat again. Okay. So we're going to use a Stokes theorem. Otherwise, it's a little bit challenging. So it's complicated. You have to. There are three pieces here. The curve. You cannot parameterize the curve by one single function. So use a Stokes theorem. This is a S, the surface described, includes, right? So by the Stokes theorem, this integral. So you write down the Stokes theorem. The curl of the vector field ds. Okay. So all you have to do is just find the curl of the vector field and the normal vector of the surface. Okay. The curl of the vector field is going to be ijk y square z square x square. A partial derivative. Sorry. So you will get negative, the first one, you get negative 2z I minus, 2xj minus 2yk, okay? Yeah, you can do that. So the normal vector n, you see the plane, the equation for the plane is x plus y plus z equals 1. Clearly, the normal vector is going to be 1, 1, 1, but divided by square 3. The unit. Yeah, we needed the unit normal vector. Okay. So this should be in the surface integral is going to be the surface integral of it's going to be negative 2z I minus 2xj minus 2yk, the dot product of I plus j plus k divided by square 3 and ds. This time the ds it's just the area element. When you multiply this out, you will get negative 2 square 3 and z plus x plus y. But over that plane, z plus x plus y is going to be 1. Okay? It's always going to be 1. So this is nothing but the area of. Now, there are still a number of students. If I put the same problem on the test, cannot figure out the area of the triangle, equilateral triangle. The area of the equilateral triangle, I don't know whether they look at my review notes or not. Okay, didn't pay attention. So if this is a equilateral triangle, so the area is going to be square 3 over 4 a square. Right? But for the triangle over there, a is the square root of 2. Okay. So here's the square root of 3 over 4, and a is the square root of 2, and then square. Okay. And then the answer will be, 4 cancel. It's just negative 1. Okay. Yeah, for that particular triangle, the side the edge length is square root 2 within the Pythagorean theorem. So it looks like if we're given 2 hours, 14 problems we can figure out. I spend lots of time on talking about other problems, related problems. I already reached to number 8, right? Hey, so C, and we're going to have 2 hours. We just only 1 hour passed. Okay. C is the path from 0, 1 to 0, 2. Okay. You have to show that this is an independent path. Okay. Show that the integral is independent of path, okay, from this between the 2 points. Okay, so in order to prove that, you have to show this. This is going to be conservative vector field. Okay, this is a line integral f dot, right, and TDS, or another notation if you already know the parameterization. Okay, and the f is going to be vector x squared plus 2xy and x squared. And this is a vector field. As long as you can prove this is a conservative, then it is going to be the line integral is independent of the passes from this 2 points. Okay, so we can just go ahead to find such f. Okay, because we are asked to prove that, right? So you just need to solve these 2 equations. Okay, let's solve these 2 equations. Integrate the first equation with respect to x. You get 1/3 x cubed plus x squared y, and plus constant, independent y. Right? Then you put into the second equation, you get x squared plus, and this is supposed to be x squared. So C must be constant. So my C should be called constant. Okay. So that means our F is going to be this function. Okay. Right. So we know that actually you can evaluate. Okay. So the integral, the line integral of this is going to be the F, the value at the 2 endpoints. It's 1, 2 minus F and 0 and 1. Okay. So it's going to be 1/3 minus when x equals 0, that's 0. Okay. So the answer is going to be 7/3. Okay. So it's independent of the paths. Okay, this is a surface integral S. S is part of the plane x plus 2y plus z equals 2 that lines in the first octant. All right, so here's the problem, right? Surface integral. How do you evaluate first surface integral? How to evaluate surface integral? Okay. So when x is a 2, y is a 1, z is going to be 2. So this is a plane. Right. I'm going to view the plane as a graph of two functions, as a graph of this function. Right. This is my f. Because I want to find the ds, right? ds is nothing but, okay? So I parameterize on this d. D is here, okay? So our d, the triangle is viewed as a graph of some function over that region d. D is the triangle in the xy plane, okay? So d, yeah, d is going to be as when x equals 2, y is 1 here. This is this is d, okay? And x plus 2y equals 2, okay? All right, so let's find out the d. ds. ds is a partial derivative of f with respect to x. This is going to be negative 1. The partial derivative of f with respect to y is going to be negative 2. So after we simplify, it's going to be square root of 6. Yeah. All right, so we are done almost. So this surface integral is going to be the double integral. And what is x? X is still x, y is still y. Okay, ds is square root of 6 dA. Very simple. Okay. And then you get a double integral over the triangle. Then you decide, okay, you can assume that integrate from 0 to 2, that's dx. Okay, for each x, the y value, look at the triangle, right? The y value is from 0. The y is going to be upper bound. It's going to be 1 minus half of x, okay? So you take square root of 6 out. So the antiderivative of x times y with respect to y is going to be half of x and y squared. Right. So I will get, I take 2 out, x, and 1 minus 1 half of x squared. Okay. So, you know how to evaluate this integral, okay? I'll stop it here for this particular problem. Find the angle between the two planes. 2x All right, so what's the definition of the angle between them? Okay, look at this. So how do I draw it? I want to draw the two planes. Okay. Okay, looks like two planes, right? So that is the angle. Okay, that's the angle. Okay, how do you find this angle? Cross product. Yeah. Okay. So look at the cross section. You have this two, right? You want to find these two angles, right? What you can have is you have two normal vectors, I think. Okay, two normal vectors. One is perpendicular to the line. Other one is perpendicular to, right? So I think these two normal vectors gives the angle because there is a possibility this one is going in that direction. So the angle you are going to get either is smaller than pi, or smaller than half, smaller than 90 degree or larger than 90 degree. That's two possible angles because it's harder to define. Even here, if you look at the plane, it could be like this, these two angles, right? So we just use a two normal vector in this picture. Theta is also here. I just need to find the two normal vectors. So n1, a normal vector is going to be 2, -2, and 1. Okay, and 2 is 1, -2. That is going to 2z. Okay. Right. So just look at the nodes. You don't need a cross product, just need a dot product. Okay. And you can tell whether the angle is larger than 90 degree or smaller than 90 degree. Okay, so n dot is cosine theta. Yeah, let's write down the formula. Cosine theta is n1 dot n2. Okay. So the dot product is going to be 2 times 1 plus -2 times -2 plus 1 times 2. And here is 2 square plus -2 square plus 1 square. 1 square plus -2 square plus 2 square. So actually the denominator is not radical, just 4 plus 4 plus 1 is going to be 9. Okay? And this is going to be 2 minus 4 plus 2. It's going to be 0. No, 0. No. 2 negative. Let me go back to check. Yeah, plus 4. Okay. So it's not giving 0. Yeah. So it's giving me 8, right? All right. So cosine theta is going to be, so this is angle is between 0 and 90 degrees. So theta is going to be after cosine 8 of 9. That's it. Okay. But so I done 10 problems.